Hi, my name is Albert Alarcon. I work at EDF, which is a French electricity producer, and I'm going to present a work I've done with my colleagues from CEREMA and Université Gustave Eiffel concerning a coupled meteorological and uncertainty interval evaluation approach for long-term noise level estimation. So here's the proposed outline. I will begin with some context and motivations. I will talk about some methodology, and it will be followed by some results on a data set. And to finish, I will conclude with some conclusions on further work. Yeah, so as we all know, meteorological conditions are of main influence when it comes to atmospheric noise propagation, and particularly seasonal effects can be very significant, especially for long periods of time. On the other hand, measurement of acoustic data for long periods are difficult to achieve, as we all know. And however, we can sometimes obtain some meteorological information over a long period. So this is one of the key ideas of this work. And the final motivation is that the long-term noise level estimation is generally difficult to achieve. Rather for road, rail, industrial, or other acoustic situations. Okay, so here's a little definition of the problem we want to tackle with. Let's assume we have a short-term period where both noise levels and meteorological factors are available, and a long-term period, which is usually a 1 year or 2 year span, where only meteorological factors are at disposal. So the goal here is to predict the noise level estimator for the long-term period, which is the LLT. And for these, we use the available long-term information, so the meteorological information, and the short-term with both noise and meteorological information. So I'm going to talk now about the methodology that we propose for this. Yeah, so the main idea here is a two-step approach, where the first step concerns the short-term period of time, and the second step concerns the long-term period of time. From the short-term period of time, what we're going to do is to try to identify groups of meteorological factors presenting significant relevance to the observed noise. And for this, we're going to apply a statistical analysis technique, which has already been presented in other congresses, like, for example, Internoise in 2016, where you'll find all the reference at the end of the presentation. And from this information from the short-term period, we are going to, let me say, spread this information through the long-term period, trying to associate sound level statistics to meteorological factors over the long period. And with this information, we're going to try to predict the long-term noise level using a uncertainty interval evaluation approach. So a little zoom here on the technique used on the short period of time, which is a statistical analysis to identify groups of meteorological factors. I'm not really going to get into the details of this technique. The details are available in the articles. But yeah, the main idea here is to have three basic steps. The first one is used to define the influence factors, meteorological factors like wind directions, temperatures, etc. The second one consists of applying a k-means algorithm, which lets us get the ranges of the associated factors. And once we have that, we're going to perform kind of a variance analysis through a Kruskal-Wallis test, which is a non-parametric test. And from these, what we're going to get are groups of meteorological factors that lead to a noise level statistic with significant relevance. Here you have a little picture that shows how the results are presented, and so these results are used afterwards on the long-term period of time. What we do now is to predict the long-term noise level, and for this we're going to use an uncertainty interval evaluation approach. So the first thing to do here is to, for each group of weather conditions obtained in the previous step, we're going to calculate the rate of occurrence of these weather conditions over the entire long-term period. And what we usually get is that the sum of these occurrences are generally lower than 1. And that means that it could be that the sum of the weather conditions over the long-term period are just not observed on the short-term period. So what we can do next is to compute the equivalent weighted level LLT tilde for the observed conditions, and also the probability of unobserved conditions to appear, P OLT, as shown in the equations from step 2. After that, we're going to write the true LLT long-term expression as shown in step 3, and we're going to finish with this LLT in between this interval, which is calculated from the LLT tilde and from the frames, the minimum and maximum values over this long-term period, as shown in this last expression. So this methodology has been applied to a dataset, and I'm going to show now some of the results. So the dataset used here has been set up coupling a parabolic sound propagation model and atmospheric model, as described in the references here. And it consists of more than 17,000 samples and covers basically a 2-year period of time. Each of the samples used in this work is composed by these 4 values, which are mean of wind direction, vertical wind speed gradient, vertical temperature gradient, and LAEC over periods of 1 hour. And you have here 2 figures showing the evolution of the sound levels over the long-term period. It's corresponding through LLT, and this is the distribution of some of the weather conditions. Here you have a vertical temperature gradient here, and versus vertical wind speed gradient. So here are some of the results of numerical experiments on the dataset, and I just want to say that the experiments consider a variation of the short-term observational length that spans from 1 month to the full duration. So this first figure shows the evolution of first the weighted LLT tilde, which is in black, and also the long-term interval, which is in between the blue and pink lines. So as we can see, the true value of the long term, which is in red, seems to be always in between the blue and pink lines, which is very good news. We can also see a speed of convergence that seems to be quite fast for the first few months and becomes quite slow after 5-6 months of observation. Also, what we can see here is that the correction of the minimum interval value is often very small compared to the equivalent weighted level of the observed conditions. So what we show here in this new figure is the evolution of the interval estimation between the blue and pink lines compared to a median estimator centered within the interval. So yeah, the convergence of this median level towards the target value presents, in this case, a very quick convergence towards the true value. So this is an interesting result. So in these new 2 figures, you can find the informations about the convergence rates of the estimators. In the left figure, we show the convergence of the interval size estimator and the median estimator error as a function of the number of observed samples. And in the left figure, we show the convergence of the interval size estimator and the median estimator error as a function of the percent of non-observed conditions. And after these results, I come now to the conclusions. Yeah, so in this work, the construction of a methodology for an estimation of long-term acoustic indicator has been proposed, and it combines both a statistical variance analysis and uncertainty interval evaluation approach. This technique has been numerically implemented in a 2-year database. And as a conclusions, We could say that the results show quite good agreement between the true long-term noise level and its estimation by this technique. We can also say that the interval estimation remains always centered on the target value, and this is independent of the observational length. And also that the use of the median value as a direct estimation shows quite good properties. Finally, I would like to say that maybe measuring high sound levels representative of long-term condition, but this appears to be quite important when it comes to the accuracy and the span of the interval size. As further work, we consider that using other databases would be really interesting, especially with strong seasonal influences, and also performing sensitivity analysis on the weather factors would be very interesting. Here are some of the references I've talked about during the presentation, so you can read them if you want more insight about this technique. And thank you very much for your attention. I'll be glad to answer your questions.